We're pleased to introduce Blanca Lara. Blanca graduated from the University of Houston Cullen College of Engineering with a bachelor's in electrical engineering in 2004. She initially worked for Boeing Military, worked on navigation systems for the F-18 and for various unmanned aircraft. During this time, she also worked with the United Space Alliance, designing and testing shuttle crew audio hardware, with Boeing Aerospace as part of the ISS Electrical Power Systems team. Also worked for General Electric Power and Water Distribution as an electrical design engineer for the LM600 product line before coming to NASA. Joined NASA as a safety and mission assurance vehicle systems engineer for power on the Orion vehicle. And as of September 2022, Blanca is the power and propulsion division supporting the EHP as the power system manager, leading lunar surface power at JSC. We see your slides, so take it away, Blanca.
Thank you so much. Thank you for having me, Matt, and thank you everybody for joining. So I'll go ahead and get started in the interest of time. Can you see my slides?
We see your slides.
Awesome. Okay, so the thing I'll cover today is, I wanted to introduce what EHP is, give a quick summary and just a couple of commentary on what the historical approach, NASA's historical approach to reliability and redundancy, and then move into what EHP is planning to do as far as reliability and what our baseline approach is so far, and then basically why NASA is interested in this reliability workshop and what we're hoping to at least what I am hoping to gain out of this workshop as well, and why we're here. So first of all, what is EHP? So EHP is the Extravehicular Activity and Human Surface Mobility Program, and it is being led out of JSC, and that is also part of the Artemis program campaign. Thus far, it consists of 3 defined elements. That is the XEVAS, which is the new generation spacesuits that have been contracts which have been awarded to Axiom and Collins Aerospace. It also consists of the LTV, which is the Lunar Terrain Vehicle. The RFP for that project was formally released May of this year. And also the pressurized rover, or PR, which is an element that will be developed in partnership with JAXA. Like John mentioned earlier, all of these elements are to be power independent. What does that mean? It means that the elements shall survive and be able to generate and recharge their own batteries or their own power systems on their own. In the future, though, we do, so while those elements will be the first elements to be on the lunar surface long term, we do expect the lunar power surface to grow and evolve potentially to something very similar, or at least we anticipate, or that's what we foresee, to something what resembles the Earth's power system, and to include many users. And that is where that paradigm shift of reliability in the way NASA is used to doing it, and then to really learn and take what the terrestrial applications have taught have taught us here, and have the opportunity to apply those, especially when it comes to reliability. So like I mentioned in previous programs, NASA's approach really has been to to build in that reliability for for our systems via fault tolerance. So in programs like the Shuttle program, the ISS, and even Orion, that really has been the way that NASA builds in that reliability. So for our the reason for that has been because the hardware and that device component expertise has been too small to really drive a quantitative requirements via the use of PRA. And like I mentioned, that paradigm is starting to shift, and there really is that opportunity for NASA to learn from those terrestrial applications, especially now that we start to think of, power as a service, and NASA being a small user of that power as a service. And so I took this chart from John's slide deck to show, again, that bottom pink left-hand, the bottom left-hand corner rectangle there is where the EHP, where my focus is, where that Artemis base camp and the NASA-led focus is going to be. But again, as we hand off to that phase alpha and then eventually grow into that phase omega, is where we really need to understand and define reliability differently than what we have than what NASA has in the past. And so going into the EHP baseline approach for reliability. So for EHP, the R&M team derives those quantitative reliability requirements to the projects. And then the projects will take those requirements and then decompose those into what we call unit failure metrics. So things like MTBF, MTTF at the box level. And then for a subset of those items, the projects will collect and track performance data to update that reliability and maintainability assessments to then drive or derive quantitative LOM and LOC requirements. And so other tools that EHP plans to use to drive this reliability into our systems, into our elements, things like reliability modeling and prediction, where the hardware reliability is analyzed using a bottom-up quantitative reliability modeling to identify potential gaps that may influence design and allow for potential reallocation. Another approach or another tool is model quantification data, where PRAs are developed leveraging the reliability analysis data provided by those hardware providers or those elements providers that include quantitative models and initial data predictions based on the best available reliability data. And then we compare those results to the reliability analysis and then compare those against the reliability allocations. Another tool is reliability design analysis, basically where the projects develop things like failure mode and effects analysis, as well as critical item lists to identify those potential opportunities for potential design improvements. Another tool that the EHP baseline approach uses is maintainability and maintenance concept. So EHP maintenance concept will provide the approach for system maintenance and supportability of the EHP hardware by providing guidance and identifying constraints. And then the last tool is a systems performance reliability analysis, where we will perform quantified reliability models and predictions that are revised and updated to reflect design levels as the system matures, and then trace that those as the traceability data becomes available, to get a better understanding of, well, this is where we started, and this is where we are. And then all of those tools will then, or all of those methods will then flow into the design review process of how we go about verifying those reliability requirements that have been developed. And so again, using the products that will then be fed into this design review process, like I mentioned, the FMEA and critical items list is what the program uses to determine hardware criticality. And that's where we identify failure modes that don't meet the applicable program reliability requirements, and then how those might become single point failures, or identify those areas where we do have single point failures, and potentially areas where the design doesn't meet that failure tolerance, that requirements that have been imposed on it. And then we might need to iterate or pivot on a different solution that might include hardware or software. And then another product is a limited life items list, and then also a EEE parts plan. And so you know, the takeaway of everything that I've shared is that EHP's reliability approach is baselined on the previous NASA program's approach. However, now that we have more mature data, we are able to make use of more of a PRA data set, or more of a PRA tool as a tool to better define and better verify those reliability requirements. And so again, thinking of that transition between the chart that I had earlier, this one between this pink box and growing from there. You know, when we think of power as a service, then that paradigm shift becomes, you know, leads us to the questions of, you know, what requirements how should those requirements be defined to expect power as a service? And you know, and then the word, you know, as we started having these discussions with other parties between NASA and industry parties, you know, we found that a lot of our terminology was even differently, right? So what really do we mean when we say reliability? Are we speaking the same terms? Do we mean the same thing? So how do we define that reliability? And then how do we articulate that the value that we would want to impose on our hardware developers, or those folks that are going to be delivering the power as that service? And then how can we leverage that terrestrial knowledge that I mentioned, you know, that that's what we know best. That's what we feel what is where we have the most experience based. So so how can we leverage those lessons learned? And then, just in general, I venture to say the EHP and even NASA's goal is to continue to remain engaged and relevant as the lunar power grid evolves to include industry and academia. And so that's why we're here today. How do we define power as a service? How do we define reliability? How do we verify that? And how do we leverage what we know here on Earth? And so I think that was all I had. Are there any questions?
Thank you, Blanca. We do have some questions in the chat. John's kind of given some responses to some of them, but I was going to promote them so you could talk some of them yourself.
Sure.
And thank you so much for giving such a great motivation for why we're having this meeting too. I think that was...
Blanca, I apologize. I thought there was still left over from my talk.
Well, I think that they're just relevant to discuss with everyone too. So if you want to weigh in,
no problem.
live,
No problem.
John, have at it. But I really wanted to promote Hunter's question here that John spoke to in the chat, and I'm curious on your thoughts on it as well, Blanca. Hunter asks, what maintainability has been built into the near-term Artemis missions, specifically 3 and 4?
Maintainability, and I'm assuming you mean as far as like R&R, like being able to R&R, I'm assuming is what that means. So as far as I understand, we expect the elements to be able to, and I could be wrong on this one, but I believe that it's 10 years. They should have a life of 10 years is what the requirement is. And I don't know if I'm necessarily answering the question, but when I think maintainability, I think the ability for it to function for X amount of time, X number of years.
I think the question's also getting at the maintenance to the system, like what would the astronauts have to change out parts, that sorts of things.
Yeah, and so I think while the intent and the desire to have that interchangeability between for all of the elements to use as similar parts as possible, I believe given that initially the crew and even the longer missions would put the crew on the lunar surface for something like 30-ish days, we really don't have a lot of time. So I don't expect there to be a lot of use cases where we have the crew doing a lot of work, repair work, and things like that on the elements.
Thank you. Yeah, that's a great answer.
I'll add on. If you look ahead to the phase alpha and omega stuff, yeah, the idea of having maintenance is much more expensive on the lunar surface than it is in the field here on Earth. Yeah. But doesn't mean it's impossible, So, I mean, I can imagine those systems being designed to have parts that could be replaced robotically, as well as VA crew. So, but that's something that's way, those requirements have not been codified.
Right, that is correct. While we do have the requirements for a robotic arm for science, a robotic arm for additional use is not something that's in scope yet.
But certainly the meat of that question, and Hunter just came up in the Q&A here to kind of clarify, certainly gets at what we're trying to do with this meeting. Maintainability of the system as Clay even alluded to in his talk is huge for reliability. And what he said is the maintainability. The question was in response to the EHP baseline approach to reliability chart that you showed earlier, assuming it's part of the baseline approach for reliability in general, how did the current architectures integrate maintainability? Anything on that, Blanca or John?
So given that it was based on my chart, I'll say since the question is based on my chart, that is as much detail as I have. It was that Hunter's question. I can follow up with Hunter and to answer that question if that's fair.
Yeah, of course. There's one more question I wanted to get to before we move on from Tim Anderson. Asking more, I guess, programmatically, are the analysis requirements and the relationships aggregated in a comprehensive mission assurance document, a program document, like, for example, Missile Defense Agency? And then second part of that question, since loss of mission and loss of crew is on the table, would we expect reliability requirements around 3 nines, like we find in safety critical avionics?
So I wouldn't say that to the second question first. I wouldn't say that that I've seen anything that any requirements that has a value of so many nines when it comes to loss of crew, loss of mission. It's we like I said, we build the redundancy we build a criticality. We work off of the criticality of the function that system is performing, and then derive a loss of crew, loss of mission requirement off of that. So they're not derived out of numbers that go out to so many nines. So that's the answer to that one. And then the first one was, if I heard that correctly, is do we build reliability requirements per mission, or was that the question?
It's asking if there's a sort of comprehensive mission assurance program document that everyone is working to, or is this something that's more in the works?
So yes, we do have and I'll say we have comprehensive hazard analyses and hazard reports that are products that are delivered, generated and delivered for each mission. So yes, we do have a comprehensive list that is derived per mission.
If I may intrude, I might suggest that's a good segue to our next speaker.
I think
yes.
it certainly is.